Hello and welcome to Physics with Amol sir. So this video is for class 12 and we are going to continue with the chapter of current electricity. Now I know there has been a very large gap between our videos, so please make sure that you have revised the previous topics. Otherwise you may find these unnecessarily confusing. So previously what we saw a derivation for EMFs when they are connected in series. Today we are going to see a derivation for EMFs connected in parallel. And we are going to talk about the very important Kirchhoff's rules. Okay, so let's begin. So now let us start with the derivation for equivalent EMF of two cells when they are connected in parallel. So here you will see EMF E1 and EMF E2. These are two cells which are connected in parallel. Okay, we want to find out what will be their equivalent EMF, and also we will find out what is their equivalent internal resistance. So when you have cells which are connected in parallel, okay, what you have to understand is for both the cells, the potential difference is going to be the same. Okay, this is the same case as we had when resistors were connected in parallel. So when resistors are connected in parallel, the potential difference across both is same. Same will be the case for our two cells. Okay, so we are going to have same potential difference. Let us call that as V. So potential difference across E1 and E2 are the same. Next, you see that the total current that is drawn from the circuit is I. Okay, and what happens is from each of the cell, the current gets divided. So we have current I1 flowing through cell E1 and I2 flowing through cell E2. Correct? And of course, you will see that when we get here I1 and I2, they combine to make the total current I. So you can write I is equal to I1 plus I2. This is the knowledge we need to have for this particular derivation. Okay, so once again, the potential difference across E1 and E2 same, but what is different is the current. Okay, current will be different for both the cells. Now let us start with our derivation. So first step, what we will do, we are going to write the current. So we will write I is equal to I1 plus I2, and let us call that as equation number 1. So I is the total current which is equal to I1 plus I2. Then we know the formula for EMF, correct? And we know the relationship between EMF and potential difference. So for the cell E1, you can write the potential difference across E1 V is equal to E1 minus I1 R1, where R1 is the internal resistance of the cell E1, correct? And from this you can write therefore I1 is equal to E1 minus V divided by R1. Let us call this equation number 2. Okay, I am sure you are able to figure this out very easily. Similarly, for the cell E2, you can write V is equal to E2 minus I2 R2, and thereby you can write I2 is equal to E2 minus V upon R2. That will be equation number 3. Okay, so equation number 1, I is equal to I1 plus I2. Equation 2 gives a formula for I1, and equation 3 gives a formula for I2. So I hope you made a note of equations 1, 2 and 3. So from equations 1, 2 and 3, we can write I is equal to, now we know that I is equal to I1 plus I2. Substitute the value for I1 and I2. We will get E1 minus V upon R1 plus E2 minus V upon R2. Notice that we have not written V1 or V2 because the potential difference is the same. Okay, and now we are going to solve this. How we will solve it? We will write this as E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. Now I am sure I don't need to explain to you what we are doing here. Okay, so then you will take E1 by R1 and E2 by R2 in one bracket. We will write it as E1 by R1 plus E2 by R2, and here we will take V common. So we will get V out of the bracket, and we will get 1 by R1 plus 1 by R2, and this is equal to I. So solve this bracket by cross multiplication and this bracket by cross multiplication. So you should get E1 R2 plus E2 R1 divided by R1 R2. here you will get R1 plus R2 upon R1 R2. Then you will rearrange, and we are only interested in finding V. So you will get V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 upon R1 plus R2. I hope that class 12 students, I need not explain how we are getting this. Okay, you have to solve all the steps and very easily you will be able to get this expression. This let us call as our equation number 4. And now let us say we are replacing our two cells which are in parallel by a common cell. Okay, so and let us say the common cell had an EMF of E equivalent and internal resistance of R equivalent. In that case, we could have written V is equal to E equivalent minus I R equivalent, that we can call as equation number 5. Once again, this equation 5 is for an equivalent EMF. If both the cells which were in parallel were replaced by a single cell, then we would get V is equal to E equivalent minus I R equivalent, equation number 5. And both these equations are one and the same. Right? So you can compare equation 4 and 5, and from that we will know that the equivalent EMF is given by E1 R2 plus E2 R1 upon R1 plus R2. And the internal resistance, the equivalent internal resistance is given by R1 R2 by R1 plus R2, which I am sure you will notice is similar to the resistors in parallel. Correct? Basically, two EMF connected in parallel will have the same internal resistance as if two resistors were connected in parallel. So what we understand is two cells when they are connected in parallel, the equivalent EMF is given by E1 R2 plus E2 R1 divided by R1 plus R2, and the equivalent internal resistance is given by R1 R2 upon R1 plus R2. Okay, and to simplify it, you can write the ratio you can get E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Okay, so this is our derivation. You have to solve the steps yourself. You will be very easily understanding what is the derivation. Okay, and these formulae you have to remember for equivalent EMF for cells connected in parallel. Okay, E1 R2 plus E2 R1 by R1 plus R2. We have solved it for only two cells. If we connect a third cell and a fourth cell, the equations still we would be able to get. They'll be a little bit more complicated. But okay, I hope this one was understood. One more thing you remember: if you are having n number of cells connected in parallel, then this equation, that is the ratio of equivalent EMF to equivalent internal resistance, that we can write as E1 R1 plus E2 by R2 plus this can go until En by Rn. So if we are having n number of resistors, to find this will be difficult, but this is a very simple formula, that is the ratio is very easy to find. Okay, so that is to be remembered. Now we will talk about the Kirchhoff's rules. Okay, when we study about current electricity, these two are very fundamental rules. So there are two rules. One is called as the junction rule, and the second one is the loop rule. Okay, so first one, let us see the junction rule. The junction rule states that at any junction, the total current arriving at the junction is equal to the total current leaving the junction. Okay, what is the meaning of this? Now, what do we mean by junction first of all? If 2 or 3 wires are meeting at the same point, that we call as a junction. Okay, so let us say we have some kind of connection like this. Okay, where 4 wires are meeting. Okay, so there is some current. Let us say this is I1, this is I2, this is I3, and the current going here is I4. So we see I1, I2, I3, they are arriving at this junction, and I4 is the current leaving the junction. Okay, so Kirchhoff's junction rule will say that the total electric current that is arriving at the junction is equal to the total current leaving the junction. That means we can write I1 plus I2 plus I3 is equal to I4. Okay, this will always be the case. whatever is the current arriving, the same current will be leaving the junction. There won't be any loss of current, neither will there be any addition of current. Okay, so this is the junction rule. Second rule is the loop rule. Loop rule says that the algebraic sum of the changes in potential across a closed loop is always 0. Now this rule is a little bit complicated to understand. Okay, so let us see. So first we will imagine a circuit loop. Now a loop should have EMF, it should have resistors, and that is what we call a closed loop in this Kirchhoff's rule. So let us imagine a very simple kind of loop. So let us have a resistor R1, then again here we have resistor R2, and these are connected to some kind of EMF, that is E1. Okay, so we have two resistors R1, R2 in a series and they are connected to a EMF E1, right? Now let us apply the Kirchhoff's loop rule for this. For this, first let us find out the current. The current will be equal to I, correct? So current I is going through R1, going through R2, and it is coming back over here. Understand that current I inside the cell is going in the opposite direction, correct? Because we always say current will go from the higher potential to the lower potential, that is through the circuit. Inside the cell, the current will go in the opposite direction. That is to be remembered. Now, what does Kirchhoff's loop rule say? It says that potential drop across this entire loop is equal to 0. That is the algebraic sum of all these potential changes is equal to 0. What it means? Now look at R1. R1 has got some potential change across it, right? There is some change in potential across R1. We can call it as V1. Right? So R1 has got some potential difference that we call as V1. Similarly, R2 has got some potential difference, we can call it as V2. And the cell here, this EMF E1, it also has some potential difference that we can call as V. Correct? So R1 has V1, R2 has V2, and E1 has V. So here, Kirchhoff's loop rule will tell us that the changes in potential, the algebraic sum of all the changes in potential will be 0. Correct? So let us put them one by one. How much is the change in potential across E1? You will see that going from this negative to positive, the change in potential is V. Correct? It has increased by a factor of V. So over here change in potential is V. How much is the change in potential for R1? It will be minus V1. Why minus V1? From here to here. See, we are going along this loop. For Kirchhoff's rules, the direction of the loop is very, very important. So we are going in this loop. So from here to here, okay, in these 2 points you can see there is actually a decrease in potential. Correct? No? Here we had high potential, here we had low potential. So change in potential is minus V1. So minus V1. Similarly, from here to here, how much is the change in potential? That is minus V2. So minus V2. This is equal to 0. So you get V minus V1 minus V2 equal to 0. Okay, that is the understanding of Kirchhoff's loop rule. Now definitely this is little bit confusing to understand. So what I will be doing is, in the next class, we are going to take a Google Meet class. So in a Google Meet class, this topic and the numericals based on this will be explained. Okay, so let us try to use the loop rule to understand in this case. Okay. So this is a simple circuit we are having. We have two resistors, one is 30 ohm, the other is 10 ohm, and they are connected to a EMF of 20 volt, right? The loop we have marked as A, B, C, D. This is a very, very simple case we are taking. In exams there will be much more complicated cases, but of course we will move to the complicated case later on. To keep things simple, we are assuming our EMF has got negligible internal resistance. Later on we will see some cases where we are actually going to put some internal resistance also. But anyways, so our loop is A, B, C, D. This is our loop. Okay, A, B, C, D, A. Let us complete that loop. So in this across this loop, we want to find out the Kirchhoff's loop rule. So what the loop rule will say? The loop rule will say that changes in potential across each of these components, that is going to be algebraically 0. Fine. How much is the change in potential across this? That is from D to A. So you will see from D to A there is actually an increase in the potential of 20 volts. Correct? Then A to B, they are basically the same, so there is no change in potential. Correct? From B to C. From B to C you will notice that there is a resistor put of 30 ohms and there is a current I that is going through our resistor. How much will be the potential change? That will be given by Ohm's law. That is V is equal to IR. So I into the resistance which is 30. How much will be the change from C to D? From C to D again it will be IR. That is I into 10 ohms. Getting the idea? So this is our loop. So now let us put the values. So from D to A, change in potential we will write as 20. Okay, because there is an increase in the potential. Then from B to C, how much is the change in potential? Change in potential is given by I into resistance. But we will write it as minus 30I. We have put the minus sign because there is a drop in the potential. Right? B was at a higher potential and C is at a lower potential. Thereby you will notice change in potential is minus 30I. Then from C to D, how much is the change in potential? That you will now immediately say it is minus 10I and this will be equal to 0. Okay, the sum of all the potential drops will be equal to 0. This is the Kirchhoff's loop rule. So one simple thing you can imagine, if you are going along the current in the direction of the current, then for that value of potential drop you should take as negative. If you are going against the current, in that case we will take the value as positive. For example, you can apply the loop rule in the opposite direction also. That is, you can say we want to go from A to D and D to C and C to B. Okay, you can do the same. You will see the overall answer you will get the same. Correct? What you will get in that case? From A to D, you will get minus 20 volt. From D to C, now it will become plus. So it will become plus 10I. From C to D, it will become plus 30I, which will be equal to 0. You will see mathematically both these equations are the same. Getting the idea? So this is how to apply the loop rule. Now the task for today, I want you to take a look at solved example number 3.7. Try to solve it. Okay, this will use the junction rule as well as the loop rule. Definitely there are going to be doubts when you are solving this. In the next Google Meet class, we are going to solve this numerical as well as the other numericals based on Kirchhoff's rules. Okay, but for today, that's all for now. Thank you.